The theme of Chapter 11 is sequences and series. We're going to start out with different types of sequences today. And our objective is to determine whether a sequence is an arithmetic sequence, a geometric sequence, or neither. And then we need to supply the missing terms of a sequence. So let's start with some definitions. First of all, a sequence is an ordered set of numbers. So some numbers in an order. Sequence, we can define it as a function whose domain or x values are positive integers, and we call them the term number. So if we have a series of 20 numbers, we would have term numbers 1 through 20. And then the y value would be the corresponding, we might call the range, would be the actual term itself, the actual numbers in the sequence, but we can also refer to them by their position in the sequence, the first term or the second term or the third term, etc. A sequence is finite if it has a limited number of terms, and infinite if it does not. That should be fairly obvious. So we've got some examples here. In red we have the term number, in blue we have the actual term itself. So if we take a look at the odd numbers starting with 3, 5, 7, 9, 11, 13, and the dot 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 means that this is notation indicating an infinite sequence. It does not continue. If the dot 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 was not there, then we would have a finite sequence. So in the blue we have the actual terms, but then we refer to them as what I've got in the red here, the term number. 3 is the first term, 5 is the second term, 7 is the third term, 9 is the fourth term, 11 is the fifth term, 13 is the sixth term, etc., etc. Alright, well, if we look at these actual terms themselves, if we have a sequence where there is a constant, and we're going to use the letter D, which can be added to each term to get the next term, we call this an arithmetic sequence, or an arithmetic progression, and the constant D is called the common difference. So what we have here is, if we look, according to this little example, 4, 7, 10, 13, 16, we ask ourselves, is this an arithmetic sequence? Is there a constant, a number that's not going to change, that I can add to the first term to get to the second term term to get to the third term to get to the fourth term to get to the fifth term, etc., etc., etc.? And the answer to that question is yes. If we add 3 to 4, we get 7. The same 3 added to 7 is 10. The same 3 added to 10 is 13. The same 3 added to 13 is 16. And we can double check by subtracting. Second term minus first term, 7 minus 4 is 3. Third term minus second term, 10 minus 7 is 3. Fourth term minus third term, 13 minus 10 is 3, etc. So the common difference is 3, and the numbers 4, 7, 10, 13, and 16 is infinite, keeps repeating, but is an infinite arithmetic sequence. Alright, the next term in the list after 16 should be fairly easy to find. Common difference is 3, so 16 plus 3 more should be 19. If we're looking for the next term after that, well, fairly simple. 19 plus 3 more is 22. Alright, let's look at the next example. Determine whether that's an arithmetic sequence or not. Is there a constant which we can add from the first term to the second term, second to the third, third to the fourth, fourth to the fifth, etc., infinitely? And there is. It turns out to be a negative number, negative 5. So if we take 50 plus negative 5, we get 45. 45 plus negative 5 is 40. 40 plus negative 5 is 35. 35 plus negative 5 is 30, etc., etc., etc. Once again, if we want to verify that by subtracting the second term minus the first term, the third term minus the second term, the fourth term minus the third term, all turn out to be negative 5. Alright, well, the next term after that, 30 plus negative 5 would be 25. Next term after that, 25 plus negative 5 is 20. Alright, here's another definition for a different kind of sequence. A sequence where there is a constant, which we're going to call r this time, which can be multiplied by each term to get the next term, is called a geometric sequence. The constant r is called the common ratio that we're using to multiply. So for each geometric sequence listed below, find the common ratio and the next two terms. So there should be some number we can multiply 2 by to get 6. Same number we multiply 6 by to get 18. Same number we multiply 18 by to get 54. And of course that common ratio is 3. Make sure you check and don't just look at the first two. Make sure you check all the numbers given to you in the list. We can verify that by dividing second term by first term. 6 divided by 2 is 3. Dividing the third term by the second term. 18 divided by 6 is 3. Dividing the fourth term by the third term. 54 divided by 18 is 3. Alright, and then to continue, it asks for the next couple of terms. So from 54, we multiply that times 3. 54 times 3 is 162. Next term after that, 162 times 3, that would be 486. So you can see with geometric sequences, the terms themselves get large fairly quickly. Alright, here's another situation we're going to use. In this particular situation, we're going to be given a formula that describes the nth term. Now the nth term is a general term. If it's an infinite sequence, could represent the 10th term, the 20th term, the 100th term, the 2000th term, whatever. And we use this notation, t sub 1 for the term number 1, t sub 2 for term number 2, t sub 3 for term number 3, t sub 4 for term number 4. So the nth term, t sub n, is described by this formula. Add 5 to 4 times the term number itself. So n represents the term number. To do that, we can make a little chart of points, and we would like to find the first 4 terms here. So n will be 1, 2, 3, and 4. And one at a time, we're going to replace every n in this equation, in this formula, with 1, and then next with 2, and next with 3, and next with 4. So replacing n with 1, we would have t sub 1, and that's 5 plus 4 times 1. 4 times 1 is 4, plus 5 more is 9. Now substitute 2 for n, so that's t sub 2 is 5 added to 4 times 2, the term number. So 4 times 2 is 8, plus 5 is 13. Continuing on with 3 times 4 is 12, plus 5 is 17. That's the third term, or t sub 3. And then for the fourth term, 4 times 4 is 16, plus 5 is 21. That's t sub 4, the fourth term. Alright, so what the sequence looks like is we have 9, 13, 17, 21, etc., 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 because it could be an infinite sequence. Question might be in your mind right now, is this arithmetic, geometric, or neither? Well, is there something we can add the first to get to the second, add that same number to the second to get to the third, add that same number to the third term to get to the fourth? And yes, you can see that we're adding 4, which shouldn't be too hard to figure out. And that's an arithmetic sequence. Alright, let's look at example 3b, and let's generate the little sequence here, where the sequence is described by the general formula n squared. So wherever we see an n, we're going to replace them by 1, 2, 3, and 4 to find the first 4 terms. So replacing n with 1, 1 squared is 1, so t sub 1, the first term, is 1. T sub 2, the second term, is the term number squared. 2 squared is 4. Third term, t sub 3, is the number 3 squared, which is 9. And then the fourth term, t sub 4, is the term number 4 squared, which is 16. What's my sequence? Well, I've got 1, 4, 9, 16. Those numbers look familiar, and they should, because they're just the perfect squares. We're taking numbers and squaring them. But it's not arithmetic. I'm not adding the same number all the way across. Well, I would add 3 from 1 to get to 4, but 4 plus 3 does not give me 9. And I can't multiply anything through here either. So this is one of these particular sequences that is not arithmetic, and it's not going to be geometric, because there's nothing I can multiply 1 by to get 4. I would not multiply that same number by 4 to get 9. Okay, so this one, it's neither. But the formula is one that we all know. The numbers are ones we all know. Perfect squares. Alright, here's another formula. We're going to generate the first 4 terms. The formula for the nth term is to take 2, raise it to the nth power, and then multiply that times 3. So let's replace every occurrence of n with 1. So t sub 1, the first term, is 3 times 2 to the first power. Don't forget to do your exponents first. So 2 to the first is 2, times 3 is 6. Let's substitute in 2. 2 squared is 4, times 3 is 12. Substitute in 3. 2 cubed is 8, times 3 is 24. That's the third term. Fourth term is 2 to the fourth, which is 16, times 3, which is 48. So my actual terms themselves, or my sequence, are the numbers 6, 12, 24, 48. Is that arithmetic? Well, no. Because I would have to add 6 to 6 to get 12, but 12 plus 6 is not 24. Is it geometric? Well, yes. 6 times 2 is 12. My common ratio is 2 then. 12 times 2 is 24. 24 times 2 is 48, and that would be geometric. And, yep, we're multiplying by 2's. All right, let's try to find the next term in the sequence, and this one's a little bit trickier. 2, 6, 12, 20, 30. What's the next term in the sequence? Well, is it arithmetic? Let's check. If it were, I would take 2 and add 4 to it to get 6. 4 would be my common difference, but 6 plus 4 is not 12. So then we ask, is it geometric? Well, actually, no. If it were, 2 times 3 would be 6. Then I would have to take 6 times 3, the common ratio, but that doesn't give me 12. What I'm going to do here is there is a pattern, but it's neither. And neither, if it's not arithmetic or geometric, does not mean it can't have a pattern. But look at the differences here. The differences between these numbers are not arithmetic, but they do follow a pattern. Difference between 2 and 6 is 4. Difference between 6 and 12 is 6. Difference between 12 and 20 is 8. And the difference between 20 and 30 is 10. Now, the difference between each term is not arithmetic, but the number that I would add to get from one term to the next follows an arithmetic pattern. 4, 6, 8, 10. So in that case, 4, 6, 8, and 10, we're just adding 2 each time to these blue numbers here, the differences between the terms. So it seems like the next difference would be a difference of 12. So to get the next term in the sequence, signified by the question mark, I would take 30, add 12 to it, and that would give me 42. So that's our first look at is the sequence that we're given arithmetic, geometric, or neither. Given a general formula, find the terms in the sequence, and then try to find the missing terms.